Here I'm going to go through an organic chemistry question from 2019. It's question 8 on the paper. And it's a question about the alcohols to start with, and it says, what is a secondary alcohol? Now, a secondary alcohol is an alcohol which has two carbons attached to the carbon bearing the OH. So, an alcohol is COH with different atoms attached to that carbon. If there's all hydrogens, that's just methanol, and that's a primary alcohol. If it has a carbon and two hydrogens, that's going to be primary. If it has two carbons and one hydrogen, then we're going to call it secondary. And if it has three carbons, obviously those carbons have to have other bonds attached as well, we'll call it tertiary. Okay, but the one we're asked for there is, what is a secondary alcohol? It's when you have two carbons attached to the carbon bearing the OH, or else one hydrogen attached to the carbon bearing the OH. And I'm just going to change them just to OR groups just for simplicity. OR is just a generic group. Okay, we're then asked to draw a graph. Okay, I'm going to do a quick sketch of a graph here. Okay, plot the boiling points of the alcohols against the number of carbon atoms present. Methanol, we know, has one carbon, and its boiling point is 65 degrees. So if I put these up, 20, 40, 60. So one carbon methanol is 64.7 degrees. There. For ethanol, we're at 78 degrees. For propane 1-ol, we're at 97 degrees. Propane 2-ol, we're at 82 degrees. That's still going to be 3 carbons, 82 degrees. Butane 1-ol, we're at 117 degrees. That's 4 carbons. And for butane 2-ol, we're back down to 99 degrees. So there's your key for that one. And we'll just finish off by labeling the axes. And this one is boiling point. So there's our graph. I'm just going to change the view now. So the next one then, state and explain the trend in the boiling points. Now, how can we explain that trend? Well, they all have the key functional group that allows them to have a really high boiling point, which is the hydrogen bonding in the OH group. The fact that you're going from methanol to ethanol to propane 1-ol to propane 2-ol to butane 1-ol, the fact that they're all increasing is because the carbon chain is increasing. Okay, so there are more points of contact between the molecules. So you got increased to there, increase because the carbon chain is increasing, so there are more points of contact as the molecules become larger, and so therefore the van der Waals forces of interaction increase there. The reason it's actually getting lower there from propane 1-ol to propane 2-ol is because you haven't extended the chain out in an unbranched fashion. So when they pack together, the intermolecular forces aren't as strong. You create a situation where the overlap between molecules of propane 1-ol are actually better than the overlap of molecules of propane 2-ol, the way they stack together. So the van der Waals there wouldn't have as big an impact. So you see a little bit of a decrease on going from propane 1-ol to propane 2-ol. An increase then again to butane 1-ol because the carbon chain is increasing. So if we want to explain the trend there, all you need to say is that the boiling point increases because you get more intermolecular forces or van der Waals between the molecules as the carbon chain increases. Predict the approximate boiling point of the next alcohol in the same series as propane 2-ol and butane 2-ol. So we're going from propane 2-ol, which is 82, up to 99. We're going to see an increase in the boiling point. We've got a jump of about 17 there. It's unlikely to be that big a jump as the carbon chain increases, so if it jumps up by 10, you've got a boiling point there of around 110 to 115 degrees. Now consider the oxidation of alcohols in which no carbon-carbon bonds are broken. Give the systematic UPAC names for the two possible organic products of such an oxidation of butan-1-ol. Okay, so we're just going to do this here. Butan-1-ol and I'll just draw out the full structural formula. When you oxidize that with sodium dichromate with some sulfuric acid, when you oxidize that, I'll just draw on the OH, you will first oxidize it. If you oxidize and then distill off the resulting product with one equivalent to the oxidizing agent, you will form the aldehyde. If you oxidize that again, or you can go direct using again the same reagents, you can form the carboxylic acid, which is butanoic acid. They are the products that you'll form. So this is butanol and this is butanoic acid. So you can form it directly by refluxing. So this is the one by reflux, and this here is distillation. Okay, identify clearly, draw the structure of the organic product when butan-2-ol is oxidized. So butan-2-ol is when you have an internal alcohol group, and when that gets oxidized, using the same conditions, you only form one product in this case, because what's going to happen here is those hydrogens will get removed and you end up forming butanone, the ketone in that case. Okay, so it says identify clearly which bonds in butan-2-ol are broken in this oxidation. So the bonds that are broken, this bond and this bond. The one I'm going from oxygen to hydrogen and the one I'm going from this carbon to this hydrogen are broken. So now the question is, draw the structure of the ester formed between methanol and propanoic acid. Methanol is here and propanoic acid is like this, and when you react those two together, this oxygen here reacting with that carbon there, and what happens is this ends up getting kicked out and that ends up leaving. So I won't go through the whole mechanism for it, but the products that are formed is this one here. So you still have your carbonyl in the middle, except now this is your methanol part, so this is called methyl, and I'm just going to highlight there's your oxygen and there's your carbon that was in the reactants, and you've got the rest of the molecule here. So that happens in every esterification reaction. So when you react a carboxylic acid and an alcohol, you form the ester. And that's the ester that you formed. How many carbon atoms in a molecule of this ester are tetrahedrally bonded? Okay, so that's a tetrahedral carbon, that's a tetrahedral, and that's a tetrahedral. So the answer to that one is 3. What are the products of the hydrolysis of this ester by sodium hydroxide? So it's now saying, if I took that and I reacted it in what's known as a saponification reaction with NaOH, what happens is the OH just pretty much goes in here, and the electrons go up and that goes back down, and you kick this product out. So You don't need to know that, but we're just going to go through that here. So you form this here, which is the salt of propanoic acid. And then you also form methanol. And that is sodium propanoate. The reason you don't form the carboxylic acid that you started with here is because you're carrying out this reactions in basic conditions. So you're not going to form the acid as a product here, you're going to form the salt, which is the sodium propanoate. So there are the two products, and that is that question there.